Hey, it's Nathan, and at this point in this little series of videos, most of the basics have been covered. So I did some like basic logic things, I did some basic set things, I did just like what the general idea of what a proof is, and in shorts I did a handful of exercises, and more of those will be posted as we go. But in this video, I wanted to talk about a particular proof method that comes up all of the time and is used in any field of math, and that is induction. So in order to talk about induction, I need to first talk about lists of statements. Several mathematical statements can be broken up into lists of statements. So instead of just proving one generic thing, you can go ahead and reformulate these generic statements as lists of individual statements. So for example, you could look at the sum of the first n numbers for all n natural numbers, or you could look at what's called the division algorithm, and we'll prove both of these things in this video. But instead of thinking about these statements as for all statements, instead we can think of them as a list of statements by just going ahead and reducing out one of the for alls of naturals. As a caveat here, I will not be covering transfinite induction in this video. That is sort of beyond the scope of what is intended for this series of videos, but now that it's on my mind, it makes sense to do a video that is aside from this series on transfinite induction. So that will add it to my list of things to do, and we're just going to keep going with just generic, you have never seen induction before, induction. As I was saying, with both of these statements, you can go ahead and reduce these statements to a list of individual statements by reducing out one of the for alls. So for example, the statement about the sum of the first n natural numbers becomes a statement about an individual natural number, and then you can just change the statement by changing the natural number that you plug into it. We can go ahead and do a similar thing with the division algorithm. So instead of saying something for all a, we can go ahead and make that a index a list of statements, and then the statement will just change based on what a value you plug into the statement. Now, if you want to go ahead and prove generalities that can be transformed into these lists of statements, oftentimes there's an opportunity to apply the principle of mathematical induction to these statements in order to get proof out from them, or recognize that they're true, or however you want to phrase that without it being too like blah. There are several analogies out there for what induction is. Some people talk about it like it's a ladder, some people talk about it like it's a set of dominoes, some people talk about it like it's an engine that just kind of, you put in something and then it kind of runs through the list and generates all of the truth that you want, or you just, anyway, there are lots of analogies here. So in order to start thinking about induction, we need to have a list of statements kind of like with those examples. So what we do is we have some natural number, which we'll call k naught, and associated to k naught and all of the natural numbers greater than k naught, we'll have this series of statements, s of k naught plus 1, all the way up to s of n, and then s of n plus 1, and so forth. And so this list of statements for each n greater than or equal to k naught is going to be all true as long as the following two things hold. One, you can go ahead and prove that s of k naught is true. And two, if you're given that s of k is true, then you can show that that implies s of k plus 1. So 1 and 2 here on the board being true give us the following diagram. And this is where a lot of people get the whole ladder or domino or engine analogy from. First, you start off with s of k naught, and from part 1 of the induction stuff, that is true. And then you can build this row of implications by using the second thing that is a part of induction. Now, we often call the first thing the base case because it starts off this chain of implications. And we call the second thing the inductive step, or the induction step. And the thing to note about the induction step is that the hypothesis of that implication, the S of k in that second thing, is often referred to as the induction hypothesis, because when we go out and write down induction proofs, when we get to the induction step, the first thing we do is that we suppose that that S of k thing, whatever it happens to be, is true, hence the word hypothesis. Another thing that's important to note here is that we can actually replace the second criteria for forming an induction argument with this strong inductive step. And so what the strong inductive step is that instead of just assuming one thing is true and seeing if it implies the next thing, we go ahead and assume that all of the things before that next thing are true and see if it implies the next thing. Now, the word strong is kind of a misnomer here, because even though the thing that you're supposing is more, you can go ahead and show that normal induction and strong induction are logically equivalent things. So if you can prove something with induction, you can still prove something with strong induction, and it is essentially the same. And I don't really want to go through and prove the equivalence between strong induction and normal induction here, but generating another diagram gives a lot of intuition for why you might believe that that is the case. I'll leave a link in the description below as well, just for an example proof of how one might prove that normal induction and strong induction are the same. I think the proof that I'll link out is from some resources from Emory University, but just drawing the diagram really quick. When you go ahead and draw the diagram, essentially it's the same. It's just that now you have all of these brackets. And whenever you think of the brackets, you think about what's ever inside of them as anded together, instead of looking at just single statements pushing the chain forward. It's like if the dominoes, instead of collapsing one by one into each other, they kind of like clumped together and then fell into the next one. It's a weird thing. It's kind of, or like a slinky. I think that would be a better image for that, because you get like parts that like come together and then they force there's a physics thing to animate and put in here somewhere, but I think of a slinky when I think about strong induction. It doesn't matter. They're the same for our purposes, and so for what we're doing, they're the same. Anyway, moving on. I've told you what induction is. I should probably give you some examples. So the first thing to prove is, the first statement that I put on the board in this video, which is about the sum of the first n integers. So when you go ahead and add up the first n integers, the proposition says that you should get the number of integers times the number of integers plus 1, all divided by 2 for any given n. When you go ahead and start an induction argument, when you're first doing induction and you're not super familiar with it, it helps to write down what the list of statements are. So in this case, we're going to let S of n be the statement that is just the sum of those n terms. Now, the base case is when we look at the statement for when n is 1. Well, when n is 1, there's only one thing in that sum, and that one thing in that sum is 1. We can go ahead and express 1 as the fraction 2 over 2, and then we can go ahead and multiply that fraction by 1. So we get 1 times 2 divided by 2, which is the same thing as n times n plus 1 over 2 in the case where n is equal to 1. So the base case holds, and we're great. Now, for the induction step, we go ahead and again, when we write down these proofs, the first thing we do with induction step is we go ahead and suppose the inductive hypothesis or the induction hypothesis. And in this case, that is just some, I think I used L when I wrote on the board. So suppose S of L holds for some L, a natural number. And now the goal is to use whatever S of L says in order to show S of L plus 1. So if we go ahead and look at S of L plus 1, and we go ahead and write out that sum, S of L plus 1 gives us the sum of 1 plus 2 plus 3 plus all the way up to L plus 1 is equal to L plus 1 times L plus 2 over 2. And so that's the equality we need to show. Now, if you go ahead and write out another one of the final terms in this sum, you can go ahead and express the 1 plus 2 all the way up to L plus 1 as 1 plus 2 all the way up to plus L plus 1. Since addition is nice and associative, we can go ahead and just add up the first L things first. And well, adding up the first L things first is the same as L times L plus 1 divided by 2 by statement S of L, which we're assuming is true by our inductive hypothesis. And then doing some factoring and a little bit of algebra niceness to make it look the way it's supposed to, we get the desired result, that the sum of the first L plus 1 terms is, in fact, L plus 1 times L plus 2, all divided by 2. So the base case holds, the inductive step holds, hence, by the principle of mathematical induction, the statement holds. For another example, and one that's a little bit more complicated to think about in the terms of induction, is just going back to the second statement that I wrote on the board in this video, which was about the division algorithm. So the division algorithm says that for every a and b natural numbers that are not zero, there exists a q and r that are natural numbers that are possibly zero, such that you can express a as b multiples of q plus r, where r is between 0 and b minus 1 inclusive. Here, Q and R are highly suggestive of what you do when you did division in grade school, and so R is just a reference to a remainder. So this proof is a little bit more technical than the previous one because on top of the actual induction argument, there will be cases to look at in the inductive step. So again, to start an induction argument, we go ahead and say this is what our statement is going to be. Our S of A is going to be the statement for a particular A, that for every b a natural number not equal to 0, there exists a q and r possibly 0, such that a can be expressed as b multiples of q plus r. The base case here is very, very quick because the statement starts with s of 1, or when a is equal to 1, and well, there are two things that can happen. One, b can be 1, and if b is 1, then q is 1 and r is 0, because there's no remainder when you divide by 1. Secondly, b could be greater than 1, and in that case, well, 1 divided by anything greater than itself will give you a remainder of 1 and no whole parts of that thing that you used to divide. So here q will be 0 and r will be 1. Hence, the base case holds. So in the induction step, we go ahead and suppose that S of A holds for some a natural number not equal to 0. And so if we do that, S of A just tells us that A is equal to B times Q plus R. For whatever B that you choose, you can find a Q and an R that do the thing that you want. In order to get something that looks like the equality that would be in the S of A plus 1 statement, we can just add 1 to both sides. So we'll have A plus 1 is equal to B times Q plus R plus 1. And here's where you have to be just slightly careful and have to think about what the remainder could have been when you divided A by B. So in the first case, well, if you divided A by B and your remainder was B minus 1, when you go through and do that calculation, you'll find that when you divide A plus 1 by B, you'll go ahead and get Q plus 1 multiples of B, right? And that's fine because Q plus 1 is a natural number, and the remainder here would be 0, which is allowed. Next, when you go ahead and think about the case where the remainder was not b minus 1, here we just do a little bit of, I guess, the closest thing that I've done so far in any of these videos to analysis, which is use inequalities, right? So if you look at r plus 1, since 0 is less than or equal to r, which is strictly less than b minus 1, because we're in the case where r does not equal b minus 1, you can go ahead and add 1 to all of the pieces of that inequality to get 1 is less than or equal to r plus 1, which is less than or equal to b minus 1. So after we've added 1 in this inequality, we can go ahead and weaken our left estimate to 0. So then we'll have that 0 is less than or equal to r plus 1, which is less than or equal to b minus 1, which is where your remainder term is supposed to be. It's supposed to be a natural number between 0 and b minus 1 inclusive. Hence, S of A plus 1 holds, and the induction step is complete. And again, you go ahead and check off the induction step, and you finish it off by saying, by the principle of mathematical induction, this original statement holds. The division algorithm comes up all over the place and has generalizations to different fields of math or different types of algebra that you would want to do. So it's good to have that in the back of your brain as we move forward. So I want to prove something about natural numbers that we usually use a lot. And I'm not going to prove uniqueness here, but I just want to prove that there is a prime factorization of a number. And so what I mean by that is that I want to show that a number has a prime factorization, but I don't want to do the uniqueness of the prime factorization. That kind of like goes beyond the point of this video. I just want to give you an example where strong induction is a more useful way of framing the proof. So the theorem here is that for every natural number not 0 or 1, either that natural number is a prime number or that natural number is a product of prime numbers. So this starts off the same way that the previous two examples did. That is, we go ahead and define the statement S of n to be the statement that n is prime or n is a product of primes. Great. Now, the base case here is not for n equals 1 because we specifically require that n not be 0 or 1 in the statement of the theorem. So here the base case is going to be n is equal to 2. And well, 2 is a prime or 2 is a product of primes can be thought of as a or b, and just 2 is a prime number is a fact that we know is true already. So a is true, so a or b is true, so the base case holds. For the inductive step, there's a little bit more work, right? So because we're doing strong induction in this proof, instead of just supposing that S of k holds for some k, we're going to suppose that S of k holds for all k between 2 and n minus 1. And so then the statement that we want to prove is S of n plus 1, which says that n plus 1 is prime or n plus 1 is a product of prime numbers. If you go ahead and suppose first that n plus 1 is prime, then n plus 1 is a prime, and we fall back into the same argument of the base case where we just had one part of the disjunction true already, and so we're done. So we don't really think about that much when we're doing the proof here. If instead we suppose then that n plus 1 is not a prime number, well, the argument becomes a little bit different, right? So since n plus 1 is not prime, then there exists two numbers a and b such that a and b are greater than 1, they are less than n plus 1, and n plus 1 is equal to a times b. So here you can't really say anything about the exact size of a and b, which is why normal induction doesn't really work here. The one thing you can say is that for any given n, the factor that you get that is greater than 1 is not going to be n minus 1. So in this case, a and b are definitely not n because we're factoring n plus 1. And so that's why we would like to frame this proof in terms of strong induction instead of normal induction. But with that remark aside, we're essentially done. So since we are using strong induction here, S of A holds and S of B holds. So either A is prime or A is a product of primes, and B is prime or B is a product of primes. To avoid the case where A is prime or B is prime, we can go ahead and just write A and B as some arbitrarily long product of primes where that product is still finite, but the product could just be one thing and the power on that thing could just be 1, right? So we can express A and B in this way. And once we do that, when we product them together, we'll see that n plus 1 is equal to this product of primes. And thus, we have the desired result for the inductive step. So hence, by the principle of mathematical induction, here using a strong inductive hypothesis, we have that the original statement holds, that every natural number has a factorization into primes. Again, I'm avoiding uniqueness here because I just want to show that one exists because it illustrates the use of strong induction in this particular case. But yes, that's essentially it. So that's a quick little overview of what induction is, and then some examples of how you would write up something using induction, both with normal induction and strong induction. Here, I will put up on the board now a list of exercises that you may want to try, all of which have some induction or strong induction argument that you can form for them. Some of them are kind of silly, like this first one about the generalized distributive property. Again, it's one of those things that you like know is a true thing, but it's a different thing to like write down the argument of why it's true, and it's just good practice to prove things that you know are true, because if you do math for long enough, you eventually get to things where you don't know whether or not they are true or not. And proving those things is a little bit more daunting and not as great of an exercise for building your proof writing skills. Also, these next two exercises, which are summation formulas, are pretty good at getting you to practice like conjecturing things and proving them, at least at a very low level. And then lastly, induction doesn't always work. And so these last two exercises are about the importance of the base case and the importance of the inductive step, respectively. Anyhow, that's basically it for this fifth, if I don't cut it into two videos, installment of this intro proofwriting series of videos that I'm doing. If you would like to see the rest of the videos that are currently in the playlist, that will be up here. If you enjoyed this video and want to see me talk about more math things, or just how I am doing as a human who is pursuing math as a thing that I want to do with my life, those things are also around in the description, and there's probably a card or two up here as well. But as always, this one was chalk, or I guess not always, but like this one in particular was chalk. I am Nathan, and I have forgotten how to do the outro, but that's okay. I will see you next time.